Hello, I'm going to go over the Central Committee entrance exams physics and the physics exam of July 18, 2022, and I will do also the further exams after that in next videos. Note that you have to have the PNAS Science Data Reference Book with you. It's a really useful book that contains constants, but also some formulas that you might need or that you might have forgotten. All right. Question 1, exercise at home. There's two figures shown here with an athlete doing exercises on a rowing machine. And there is a bench that can roll over a beam here. And a rowing movement consists of two parts A and B. This is the starting position, and the athlete will push himself to the left. At the same time, he will pull on the flywheel via this cable, and that makes this flywheel spin faster. It's heavy wheel used to store kinetic energy. And from the rear position then, he will pull his legs towards his body so that he's back in the starting position. And during this part, the rotational speed of the flywheel decreases due to friction. Then there is a figure given here with the distance between the bench and the back of the beam. Okay, so this is their convention, their definition of the distance x. Then, using this figure, explain whether the athlete reaches a higher speed during part A or during part B. So let me copy. So where is, well, first of all, this gives x as function of t. So you see here, this is the maximum x that can be achieved. That means that he is forward here. And this is the minimum x, where he's close to the end of the beam here. And speed is given by the slope of distance over time. So we can look at the slopes here. Well, first, what is actually A? So A was the first part that x is decreasing. So x is decreasing here. So this must be part A. And then the part that x is increasing again will be part B here. So what we then have to do is just figure out which slope is steeper. So you can see roughly here what the slope is. And you can already see by how I turn the ruler that I need to turn it at a steeper angle here. So obviously, shall I just remove this? We can just say that the slope in A is steeper. So this is on A. Slope in A is steeper than in B. So higher speed during A. Then question 1b. they show here a velocity diagram of some rowing movements. So velocity over time. The maximum distance over which a bench rolls during A of a rowing movement is called Xmax. This Xmax can be determined from both figure 2 and figure 3. Explain for both figures how this can be done. And you don't need to perform the determination. Okay, well, let's first look at the distance over time. Part A starts here, which is the part where the distance x decreases. And then the peak to peak basically will be the total distance traveled. So figure 1, or figure 2, it's just the peak to peak. During segment A. And then about velocity diagram. Well, let's analyze this a little bit. Here, the velocity is positive, means it's moving to the right. And section A of the movement is moving to the left, which means a negative velocity. So starting here, it will start to move in a negative direction. It's faster, faster, faster until it reaches some peak velocity here. But then it starts to deaccelerate to the left, but still in a negative direction, until a point here where it becomes positive. So this will be section A, this will be section B, where you move to the right. And one thing you learned in kinematics, because, well, velocity is delta x divided by delta t. So in other words, delta x can be found from the velocity. And if you do this for like a non-constant velocity, then you need to kind of make the sum over all these distances you travel, which is the integral, which corresponds to the area here. It's basically adding many small areas phi times delta t. But we don't need to do all that. We just can say from the area during, so the area of phi versus t during A. Okay, and you see it's negative, and that shouldn't be surprised because the person is moving to the left. Then the resulting force on the athlete and a bench is not constant during the rowing movement. Explain at which times in figure 3 there is no resultant force acting on the athlete and the bench. Okay. Well, so no resulting force. Now, given that this is also the mass of the bench and the athlete together times the acceleration, that means that this happens when A is equal to 0, which means that delta phi divided by delta t is 0. And if you take these time increments smaller and smaller, you arrive at the instantaneous velocity. So the slope of v as function of t has to be 0. Then we can see where this happens. Well, here, somewhere in movement A, and you see that the instantaneous velocity is 0 here. It just goes from negative to positive. And here it is close to 0, but not exactly. Then here, somewhere in the middle of movement B, here and here, and these 3 points. So that happens when this is 39, this is 39.5, so this is about 39.5 something, between 39.5 and 39.6, so say around 39.5 seconds. And here this is 41, this is 41.5. So say 41.6. Five, 7, 5. So between 5 and 7, 5. So say about 42.65. This is actually probably 41 point. It's a little bit closer to 41.5. I would just say 41.5. Okay, so for the rotational energy of the flywheel, we have this equation. So it's proportional to the frequency squared. And here it shows the rotational frequency of the flywheel as a function of time. So we see the frequency goes up and down. So the energy stored will go up and down. The endurance power of the athlete is here understood to mean the power that he transfers on average to the flywheel over a long period of time. Endurance power. Determine this if the rotation frequency continues as shown here. First, determine how much energy of the athlete is converted into rotational energy of the flywheel during one rowing movement. Okay, let's do that first. Well, during one movement, the difference in rotational energy given by can be found from the frequencies here when it's high and when it's low. So say that energy transferred will then be, say, if you look at one movement, k frequency initial minus k frequency final squared. So this is equal to 1.2 times, I can factorize k here. This is 22.5 squared minus 10 squared. And let's calculate that. Oh, did something wrong there. Wait. Okay, 20 squared minus 10 squared equals times 1.2. That's 487.5 joule. And I just keep these significant digits for now, though in the end you can only take two. And so that's the first part. Then we need to figure out what is the time period of one movement. So the time between here and here. We can probably from the previous you can also find it, but you might well find it here. Actually, it seems to continue here. So from here to here is 1, 2 periods. So the period let's call that T is then 38 minus 32, but then divided by two periods. So that is then 3 seconds. So then for the power, we find that it is this energy transferred in one movement divided by the period. So we get 487.5 divided by 3. 487 divided by 3. And now I just want to keep two significant digits because of the 1.2. So I can write this then as 1.6 times 10 to the power 2 watt. Question 2 is about sound. Sound waves can produce flashes of light in water. So we have a glass flask and two mini loudspeakers here and some tone is generated here with an amplifier, and these sound waves cause pressure in water to alternate, increase and decrease, alternately increase and decrease. The water contains air bubbles that expand when the pressure in the water decreases. The air pressure in the bubbles also decreases sharply, which will happen when they expand. When increasing water pressure, the bubbles are compressed, storing energy from the sound waves. Okay. This happens until the stored energy is released as a flash of light. The flashes are emitted with great regularity depending on the sound frequency chosen. The sound wave passes through the glass wall of the flask into the water. Okay, that makes sense. Explain whether the wavelength of sound in glass is less, greater than, or equal to that in water. Well, the wavelength of sound as well as the speed of sound is different in different mediums because of a different intensity. And the frequency of the sound, or the period, is basically independent. That's just related to kind of the driving motion of the loudspeaker. or the tone generator. It just follows that. So different wavelengths, and the thing I just tend to remember, and from that derive any other relations, is saying that the speed of sound is, or any wave, is the lambda divided by the period. So the wavelength is proportional to the speed. So then let's figure out for glass and water what are the different speeds. So we go to the Bina's book for that. And the Bina's book is in Dutch, unfortunately. I have no idea how people, if there's some alternative in English for this. I have to look that up. But be very familiar with the table of contents here of the physics part. There are like 7 to 35 tables, and you need to be able to navigate this pretty well. And that comes with practice. There's actually a section about equations, formula in physics that are also useful when you have a blackout or forgot some basic equation. So let's, what was I going to do? The speed of sound. Okay, there's a section here about geluid, which is sound, and about the speed of sound in different mediums. And here we have glass. So in say phi glass is, it's a range. That's probably because glass is probably not so well defined. And we look at it at 293 Kelvin, so at room temperature, times 10 to the power 3 meters per second at room temperature. And waters, we look under the liquids. And also let's look at the same at room temperature. So phi water is 1.484 times 10 to the power 3 meters per second at room temperature. So phi class is actually much faster than the speed in water. So lambda class is also larger than lambda in water. So that should be the right answer. The glass flask is spherical and has an inner diameter of 6.2 centimeters. The frequency of the sound is chosen in such a way that a standing wave is created in the water in the flask. Steady pressure antinodes are created along the connecting line, namely at the interface between water and glass, and in the center of the flask. So you have something like antinode, node, and then antinode. Remember, antinode is where the amplitude is maximum. And then say this is the boundary of the or interface with the class. And this is 6.2 centimeter. And this is basically one wavelength, or the distance here between nodes is half the wavelength. So, and what about frequency? Well, again, I start with the equation I always start with, but I just can convert the period into frequency. So the speed is just lambda times the frequency. So the frequency is just the speed divided by the wavelengths. And this is water. So it's 1.484 10 to the power 3 divided by 0.62. 1.484. And this is equal to 2. I keep two significant figures. That's how accurate the wavelength is given. So times 10 to the power 4 hertz. Okay. Each of the loudspeakers used has an electrical power of 1.5 watts, but only 2.2% of this is converted into sound, which is transmitted equally in all directions. Suppose that you only have 1.5 watt loudspeakers. Only one loudspeaker is switched on, and that reflection and absorption of the sound can be neglected. Calculate the distance from the loudspeaker at which the intensity of the sound is 1.4 times 10 to the power minus 1 watt per square meter. Okay, so we have, what is this, 2C? We have, say, a P effective power of 1.5 watt times 0.22%. So let's first calculate that. Point 0.22 divided by 100 is 3.3. I just keep one more significant digit, then maybe you can, for an intermediate calculation, 10 to the power minus 3 watt. Now, intensity is given by the power per square meter. And so in this case, the sound will be propagate in all directions in a in three-dimensional space, so in a sphere. And that surface area is 4 pi r squared. And so this is then the effect, this should be the effective power. And they want this to be equal to 1.4 times 10 to the power minus 1. So that means that for the so this I is given, we know the effective power, so we can just solve for R here. So R would be equal to multiply both sides by R squared and divide by I. Effective divided by 4 pi times I. And then I need to take the square root. So 1.4, oops, 3.3 times 10 to the power minus 3 divided by 4 pi times 1.4 times 10 to the power minus 1. That equals 1 point, and I keep, oh, I should take the square root. 4.3, keeping two significant digits, was 10 to the power minus 2 meter. All right, that's correct. An air bubble has the temperature of the water and a pressure of given here. During expansion, the diameter of the air bubble can increase 13 times. The temperature in the bubble drops by 1.6 times 10 to the power 2 degrees Celsius. Calculate the pressure in the air bubble if it has a diameter 13 times as large. So the temperature in the bubble drops. That's interesting. It would probably quickly get the same temperature as the water, but I guess they just ask for this right after this expansion happens. So, and yeah, I assume the temperature of the water. I already forgot the day. Oh, temperature 20 C. That's also what I used for these speed of sound calculations. So with these things, it's probably good to see what remained constant and what changed. So and we keep our ideal gas law, PV divided by T is constant in mind. And I've seen many exams that make use of this. So the pressure, uh, well, the pressure will change, and that is actually being asked. So say the P final is kind of the question mark. The P initial is 1.0 times 10 to the power 5 Pascal. Well, what about the final temperature? Well, we are 20 C, and then it drops by this, which is 160 degrees. So you go from room temperature or from 20 degrees to minus 100. Well, let's keep Kelvin. So you go from 293 to 160. So that's a difference of 100 and 33 degrees, well, Kelvin. And so T initial, of course, is 293 Kelvin. And what about the volume? Well, they say the volume, even though they don't give the initial volume, they say it increases 13 times. So that just means that the final volume divided by the initial volume is 13. It's proportional to the volume is proportional to the diameter cubed, right? Or the radius cubed. Okay, so we have P final divided by T. Final is initial equal to the same expression for the initial values. So P final is then P initial times the ratio of the volumes, Vi divided by V final, times the final temperature divided by the initial temperature, right? Basically, the pressure is proportional to the temperature, inversely proportional to the volume. And now we just substitute. So we get this. And this is actually not correct. They say the diameter increases 13 times. So the volume actually, I should have a cubed here. The volume is the cube of the diameter, or proportional to the cube of the diameter. So you get times third, and then this is actually the inverse. So I get V initial divided by V final. So I get actually 13 to the power negative 3 times the ratio of the temperatures. So 133 divided by 293. Okay. So 1.01 1.0 times 10 to the power 5 and times, this put parentheses just in case, 13 power times 133 divided by 293. That is 2. I keep two significant digits. Times 10 to the power 1 Pascal. A light detector is glued outside of the flask. The flashes of light appear at the center of the flask. It turns out the detector receives so many photons for each flash. The energy reaching the detector of each flash is this amount of joules. And we assume the emitted light is monochromatic. Calculate the wavelengths of the emitted light in air. Well, what you need to know here is that the energy of a photon is tied to its frequency. This is a fundamental relation you definitely have to be aware of. And the constant in between is Planck's constant. So, since we know how much energy these photons consist of, we can figure out actually what the frequency is. So, let's just first calculate the frequency from what we know. So 8.5 times 10 to the power 4 times h times the frequency is equal to 4.1 times 10 to the power minus 14 joule. So the frequency is okay, let me just write it out one more time. Minus 14 divided by 8.5 times 10 to the power 4 times the Planck constant. And then what's Planck constant? Go to Venus here. And that must be one of the first table. I probably should know it, I remember it, but H is 6.626 times 10 to the power minus 34 joule. So going back to my calculator, I need to divide this by 6.626. So I get a frequency of 7.3 times 10 to the power 14. Actually, let's keep a little bit more digits here. I keep one more digit than would be required. So I keep 3 times 10 to the power 14 hertz. Now I can, from this, go back to, need to find the wavelengths. Again, the equation I just remember is that, the speed of light, the wavelength of light divided by the period. So it's lambda times the frequency. And frequency is given here. Lambda is then the speed of light divided by the frequency. And the speed of light is probably, okay, in 3 decimal places, I can just use 3.00. times 10 to the power 8 meter per second divided by that frequency. And so go to my calculator. That is actually a number that fortunately comes out in the visible wavelengths, which is good if you find something that's far out. You should probably double check your calculation. I keep one significant digit. Meter. The thickness of the wall of the flask is 4 millimeter. The detector has a receiving area of 1.3 square centimeters. Of the light aimed at the receiving surface of the detector, 70% is not registered due to reflection and absorption. Calculate how many photons a bubble emits per flash. Okay, so let's try to sketch it a little bit. So we say we have the center of the bubble here, and that emits photons in all directions. That's actually what they are asking for. How many these are per flash. But what we know really is, so there's a detector here, some apparatus with a surface area A that picks up just the percentage of the photons that arrive here. So now this is two-dimensional, but in 3 dimensions, what you actually will receive by surface area here is the ratio of the surface area of the detector and the total surface area of the sphere of a certain radius. So we have a radius r here, given by how far the detector is from the bubble. Okay, so let's say that and f here is the number of photons that is emitted, and let's say n in here is the number of photons arriving at the detector opening. Detector opening. So as I mentioned, then we have that n in is equal to nf, the total number of photons that are emitted in all directions. Let me write it like this. Times the area A, which is 1.3 square centimeters, divided by the surface area of a sphere. Okay, and the radius is the distance from the bubble to the detector. So it consists of the thickness of the flask and how do you find so this radius here we know r is, what was it, 6.2 centimeters. Yeah, 6.2 centimeters divided by 2 is 3.1 centimeter. What else? Oh, plus the thickness of the flask itself, of the wall of the flask. So that's so this is in centimeters. So 0.4 is then 3.1 plus 0.4, 3.5 centimeter. So I can okay, and then what is the number of photons that are actually detected? Let's call that ND. Oh, it's a little bit messy. Say number of photons that actually goes through the receiving surface of the detector. So detected. And that's actually the number that given here, 8.5 times 10 to the power 4. But it's equal to 0.17 times n in. So now we can combine this all. I mean, you can always first calculate what n in is and then nd, but you can kind of combine this all in one formula. Let me first then say that this is equal to nd divided by 0.17. nd is known, r is known, a is known, but the unknown is nf here. So we kind of rearrange that, getting a little bit out of space. I multiply both sides by 4 pi r squared and divide by a. So I get the master equation and the divided by 0.17 times 4 pi r squared divided by a, the surface area of the detector. Okay, let's substitute 8.5 times 10 to the power 4 divided by 0.17, and we have a 4 pi, and then 3.5 times 10 to the power minus 2 squared divided by a, actually I can just keep it in centimeters because this is a ratio. Well, never mind. Where was I? 1.3 times 10 to the power minus 2. Centimeter squared. No, no, no. Let's 1.3 centimeters squared. Convert that into meter squared. Is 1.3 times 10 to the power minus 4 meter squared. So, wow, this could be all very error prone. But let's try it. In principle, the method here should be okay. 0.7 is a 17% times 4 times pi. And now I just do 3.5 squared divided by 1.3. Divided by 1.3. That is how many? Keep 2 significant. 5.9 times 10 to the power 7 photons. So quite a lot more than you detected, as very much makes sense. And that's actually wrong. Why is this wrong? Okay, now I'm wasting time. No pressure. Let's go over it again. The number of photons arriving in front of the detector will be equal to this. That's fine. And the number of actually atoms that reach the detector inside is much smaller than that. 70% is not registered. Okay. I see the mistake, guys. All right, I get some points deducted. A no A score here. It actually, it means that 0.83 is registered. 0.83 is registered, so this should be 0.83. 83% of all the photons that arrive at the front, the detector, are actually detected. Okay, so I'm not sure if I would have discovered this mistake if I would review it myself. So get this out of the way. I have to do it again. I can just multiply whatever I found by actually the ratio here, but let's just do it from scratch. 8.5 divided by 0.83 times 4 times pi. And again, I just do 3.5 squared. And this I just divide by 1.3. So I get 1.2 times 10 to the power 7. And that sounds more familiar. Yeah. All right. Grinding on natural gas. To be less dependent on Russian natural gas, one can import natural gas from America. For transport, natural gas is deeply cooled to minus this, where it becomes a liquid. And then this liquefied natural gas is transported by tankers. The tanker has 4 circle tanks. In total, the tanker can transport this amount of liquefied gas. And due to evaporation, there is some gaseous natural gas above the liquid in the tank. This can create slight overpressure with respect to the outside air. And this overpressure actually serves to prevent air from entering the tanks in the event of small leaks, which would create an explosive mixture. Explain whether the risk of explosive mixture being formed decreases or increases when the temperature decreases in the tank. Well, what happens if the temperature decreases? Well, we know one of the gas laws that I always forget which of the 3 it is, but let's just look at ideal gas law. I think P times V constant is the one of Boyle, and P divided by T was that Charles law? Sorry, I should stop talking. Let's just use this. This is constant. So we have this mixture there. And that means that if the temperature decreases, so if T decreases, the pressure P also decreases, since the volume of a tank doesn't change. So V is constant. So apparently this overpressure is actually necessary to prevent prevent leaks. So this means the risk of leaks is actually increased. The temperature in the tanks is what I was already mentioned. Some heat exchange environment still occurs. That's caused by leakage of heat through the insulation layer. This heat leaks amounts to 350 kilowatt. So that's how many joule per hour. Sorry, how many joule per second? So 350 kJoule per second is leaking. To compensate for this, you need to vaporize the natural gas regularly. And to evaporate a quantity of heat of 0.5, 1 10 to the power 6 joules required per kilogram. This heat is used to evaporate, to pull apart the molecules of the gas. And then this is the density of the gas. Calculate the number of cubic meters that evaporates at 24 hours. Okay, well, it's 350 kilowatt. So what kind of energy are we talking about then in 24 hours? So let's say, so this joule per second, so 1 hour is 3,600 seconds. That's the number I at least always remember. Then this is the number of joules times 3,600 times 24. I also need to multiply with 10 to the power 3. So 3, and let's just keep these significant digits, times 10 to the power 10 joule. Then we can find out how many kilograms is required, because this is kind of latent evaporation heat per kilogram. So we need that number 0.5 on that. I 3.024 times 10 to the power 10 divided by 0.51 times 10 to the power 6. That is 5. And let's just for now keep 3 significant digits. 10 to the power 4 kilogram. So evaporation of this will require this amount of heat. We need to figure out what that is in terms of volume. So the density is mass times volume. So volume is just equal to mass divided by the density. So it's this divided by 4.23. Let's calculate that. 5.929 times 423. That's 140 meter cubed. The heat that is extracted from liquefied gas during evaporation is needed, among other things, to increase the internal energy of the gas molecules. Using molecular theory, explain that the internal energy of the gas molecules in the vapor increased during vaporization. So that's kind of a general kind of kinetic theory explanation? Well, I need to break the bonds between the molecules in a gas, which increases their potential energy. You kind of need to pull them apart. So potential energy increases, which increases the internal energy. Now, the kinetic energy is remaining the same because during vaporization, the temperature stays constant. 3D, the density of natural gas at room temperature and air pressure at sea level, so-called standard condition, is this. So that's in a gas form. A Dutch household consumes so many cubic meters of gas each year. Calculate how many cubic meters of natural gas is produced under standard conditions if all the liquefied natural gas is evaporated. Neglect the amount of gas used to cool natural gas during transportation. Well, how much do we have in the ship? Let's go back here. We have this amount of liquefied natural gas. So we can use rho, the density of liquefied natural gas, is the mass divided by the volume. So the mass we have is just rho times the volume, and rho is given by 423 kilogram per meter cube times the volume here. So that's 423 times 1.2, that's x to the power 3, is 5.076. I just keep more digits again, times 10 to the power 7 kilogram. And then if this all turns into gas, we need to use the density of the gas form. So again, we use the same equation. Now we need to find the volume. So the volume is mass divided by rho is 5.076 times 10 to the power 7 divided by 0.776, and this equals to 5.076 10 to the power 7 divided by 0.776 is 6.5 times 10 to the power 7 meters cubed. How many households of this can be supplied with gas for 1 year? Let me see, this should be fit in here because that's not so difficult. One household has this, so you just need to, or you can supply 6.5 times 10 to the power 7 divided by 11.69, 6.57 divided by 1169 is 5 times 6 times 10 to the 4 households. Question 4 is about an NTC thermistor. This is a resistor whose resistance value decreases as its temperature increases. And this is due to heat development. In this case, more heat will reduce the resistance. And figure 1 is a circuit where this is included. There you see a voltage source with a small resistance R here. Then they say after it's closed, the temperature of the NTC rises. Oksana measures the voltage across the NTC and the current, and the temperature then does not change any further. And here are the measurements. And question 4a. Determine in which direction the current is traversed during the test, from D to E or E to D. As is stated here, the temperature rises after you started the experiment. So T rises, which means the resistance decreases, which means the current increases. So which one has the highest current? Well, E. So D has the lowest current. So the experiment started at D. And I guess you can also figure out what just using Ohm's law, what the resistance is in D and E. Actually, see the current difference is very large, and there's just a small voltage difference. So I'm also pretty sure that at E, the resistance is lower than at D. Show that the voltage of the voltage source is equal to 7 volt. So we can, well, let's copy the circuit. And with these things, a systematic way to figure out and to solve the circuit, if you will, is to do a node analysis. And you just look at the circuit with the different components, the source, the resistor, the other resistor here, and just define nodes between them, nodes. So this would be a node, this would be one. I just assume the switch is closed. Here's a node, and then these and all the lines that are connected, they just form one node. I can then arbitrarily define that one node is at 0, and then so they ask about the source voltage. So now we're going to assign voltages to, or potentials, I would say, to each node, basically Ohm's law, everywhere we can. So this node will be at Vs, the source voltage across the source. And this node will just be, well, let's call that V here. You can see this is also across ground. So this is actually the voltage that is plotted here. And then we have a current I going through it. Ohm's law across this node tells us that the difference between Vs and V is the potential difference over the resistance, which is the current times the resistance. So we have Vs minus V, I call this V, is the current through that resistor. The current is given here for different voltages. Say if I approaches 0, then the source voltage minus the voltage over the thermistor is 0. That's basically because something like this would happen if this resistance becomes very large. Say you, in this case, if you cool it down. And in the graph, that would mean you reduce the current. Well, what happens if you extrapolate this to I is 0? Well, you can see because of the lag, it's very wiggly. But it seems plausible from here that it is 7-fold. So extrapolation in figure 2 shows that V source 7.0 volt. Determine the magnitude of the resistor R. Okay, well, we already did this simple node analysis. So the difference between the source voltage and the voltage across it is I times R. And just let's apply it to one of these points here. Let's just take point E. So what did we have? We have V source minus V is current times this resistor R that we want to know. And figure 2, the I equals, this is 0.35, and then they divide it in 10. So this distance here is 0.5. So a minor unit is, so the minor for grid here is, because these are 10, is 0.05. And we have 1, 2, 3, 4, 5, 6 of them. So times 6. No. This is 0.05. And the minor grid is dividing this in 10. So the minor, but I already counted 6 of them. So you get 0.030 as this distance here. And then plus 0.3. So I conclude at point E, so I use point E, that the current is 0.33 amperes. And the voltage level there, this one is more easy. You can just, one minor grid here is 0.01. So you get 6.79 volt. And we know Vs is given 7.0, and we can just apply Ohm's law. Okay, so let's keep two significant digits. So we get 6.4 times 10 to the power minus 1 ohm, right? So this is basically 64 ohm. No, not 64 ohm, 0.64 ohm. So really small. The electrical power that the NTC converts into heat, that's of course through the equation for power is a potential difference times current, V times I, depends on the resistance, and thus the temperature, since we know the resistance depends on temperature. And then figure 3 shows this as a function of temperature, the solid curve here. So that's the heat generated, the electric heat kind of converted, the electric power converted into heat. Determine the temperature of the NTC corresponding to the state of point X in figure 2. Point X. So in point X, we have I equals 0.25 ampere. And the voltage is here 1, 2, 3, 4. So 0.684 volt. That means in this NTC, the power generated, converted from the electrical power will be 0.25 times 6.84 is 1.71 watt. Okay, so now we need to figure out at what the power is 1.71. So this is 1.5, this is 1.7. It's like two minor grids above 0.71. So somewhere here. So figure 3 tells us that T of the NTC equals about 33 degrees Celsius. For E, explain. Oh, wait, first they have a little story here. The NTC releases heat to the environment as a result of the temperature difference. That makes sense. So heat is generated, but this heat could conduct out, for example, through the kind of physical, whatever physical connection is made, or even the air around it. So heat is conducted out for the prevailing ambient temperature. Figure 3 shows the power produced by the NTC as a function of its temperature by the dashed line. So the ambient temperature kind of gives a differential with the temperature of the resistor itself. And because of the temperature gradient, some heat transfer will happen. And then from figure 3, you can then read off how much heat is then dissipating to the environment. They call that being produced. Oksana heats the NTC using a flame. The switch is closed, and as a result, the temperature of the NTC rises to 120 degrees Celsius. Then she removes the flame. So, explain whether the temperature of the NTC rises or falls after removing the flame. Well, what happens at 120 C? So, the heat generated, the electrical heat generated is around 9 watts. But then what is dissipated out to the ambient is something lower. So as a matter of fact, there is a net. So the P what do you say, in, I call that in, is larger than P out. So this you can say see figure 3. So this is about 9 watt, and this is about 8.3 watt. So what does that mean? Well, the T and NTC will increase. There's a net heat flow in. Question 5, E equals mc squared. So this is the famous equation from Einstein that mass represents an amount of energy and vice versa. Scientists have investigated the correctness, and they used the reaction in which silicon-28 captures a neutron, and this creates silicon-29, so one nucleon more, and releases 2 gamma photons. And then the energy of these 2 photons together should then correspond to this mass difference. And then in the first experiment, they determined the mass difference between these two. In the second one, the wavelengths of both photons, which would give the frequency and the energy. And they were able to prove the correctness with an accuracy of 1 part in 10 million. The first experiment, the mass difference between the two was determined via a frequency measurement. The atoms were ionized once, then accelerated, then brought into homogeneous magnetic field. The speed of the silicon plus ions was perpendicular to the direction of the magnetic field. This put both ions in a circular orbit. Explain why the orbit of the ions is circular. Well, the knowledge required here is that the force that a charged particle experiences is given by, it's also called the Lorentz force, with an L, is q times the speed times the magnetic field. Q is the charge, which in this case is positive. Now, so let's draw it. So we have a magnetic field, and let's try to draw it in a way that the magnetic field goes into the paper, and let's indicate this by a circle with a cross. So something like this. And this means into the paper. So then you have your ions coming in, and for the directionless force is given by the right hand rule. Actually, yeah, in high school physics they don't write it in vector form. In vector form, this is so-called outer product. The direction of this force can be determined by the right hand rule. If you figure it out, then this is the direction then of a phi outer product B. And since Q is positive, this is also the direction of the force. If Q is negative, if this is, say, an electron, then the force would be in this direction. But you can see the force is perpendicular to, so force is perpendicular to the speed, or the velocity, I would say. So this will give rise to a circular motion. And this B field in this area also is assumed to be a constant, always, again, pointing down into the paper. These researchers are able to very accurately measure the frequencies at which the ions rotated. The frequency f at which an ion with charge q rotates with strength b depends on its mass and not on its speed and the radius of the circle. Actually, the frequency is bq divided by 2 pi m. Derive this formula from formulas in Venus. Well, there's a relation between the centripetal force, the mass, and the speed that you have to remember. Actually, the force is given by centripetal is m times v squared divided by r. So v is the speed, m is the mass of the ion, and r is the radius of the circle along which will travel. And this force then, as we saw, is given by this by the Lorentz force, which is Q times B times phi. Now, how does the frequency come in? Well, we know that the speed along a circle, phi, is just 2 pi r, which is the circumference of a circle of radius r, divided by a period, how long it will take to travel that. And 1 over t is the frequency, so this is the frequency times 2 pi r. So I guess this might be actually the formula that we can find in Binas, in the chapter about physics formula. Okay, so from this we learn that the frequency is then the speed divided by 2 pi r. Well, what do we know of the speed? This equation has to be satisfied, so let's call this 1. Then we can isolate the speed here. So we divide both sides by v and multiply both sides by r over m. So we get for the speed is r times q times b divided by m. Okay, so what now we can substitute this here, and then you can see that r actually drops. So from this equation, 2 then follows that the frequency is rqb divided by m, then divided by 2 pi r. So these r's drop here. So you get qb divided by 2 pi m. The value of B was 8.5 Tesla. Calculate for one of the ions the frequency at which it rotated. So the frequency equals BQ divided by 2 pi m. And we can just take 28 silicon, so mass number of 28. It's an ion, but the mass of the electron is insignificant. So we have 8.5 times the charge of this ion, which is the elementary charge, 1.602, I happen to remember that, times 10 to the power minus 27. Okay, divided by 2 times pi times the mass of this, well, that's 28 times the mass constant. Which you can find in the Binas table 7b. Not my. Okay, sorry. Minus 19, of course. Minus 19. We need to be really careful. Okay. So 8.5 times 1.602 divided by that thing there. Careful. 1.66. That is 4.6 times 10 to the power 6 hertz. Wait, did 4.7, of course. Okay, not sure if they subtract a point for that. It's 4.7. Because the mass of the neutron was known exactly, the researchers were able to determine the mass difference delta m exactly from the measurements of the frequencies. And it's given here. Uh, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10, that's what I mentioned, right? 10 significant figures. Okay. The wavelengths of the gamma photons released in the capture reaction was measured very accurately. And we have the results here. The energy of each photon is also calculated. Because the values in Venus are not accurate enough, the table below lists values of some constants. Okay, that's fine. Then these show that the calculated energy E1 of the first gamma photon corresponds to the measured wavelengths lambda 1. Well, so we have the lambda, so lambda 1 will give a frequency 1. And since we know that the energy is of a photon is Planck's constant times the frequency, this will give a energy. All right, so what's the frequency? Again, if you forgot the equations, you can just derive it. So, I start with the speed of light is equal to the wavelengths divided by the period, which is the wavelengths times the frequency. So we can find the frequency equals then the speed of light divided by lambda 1. Now I can calculate this first, but see, I want to prevent as many calculations as possible to skip that to the end. I can then say that the energy equals Planck constant times the frequency. So that's h times c divided by lambda 1. And this is in joule. And if I want to convert this into EV, then I need to divide this by also at the elementary charge. So 1 EV is related to energy a electron of this charge gets if accelerated over 1 volt in EV is then hc divided by lambda 1 then divided by this elementary charge. So I can just substitute it. I get h 6.6 260,690. Then times the speed of light. Divide by the wavelengths given here. Then finally times the elementary charge to convert from Joule to EV. Oh, 21765. So I get 3.539,19825. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's keep 10. 10 times 10 to the power 6. So let's compare here. Let me move the decimal point by 6. 1, 2, 3, 4, 5, 6. So it comes out here. So I remove this decimal point. Oh, and the unit should be EV. So that's exactly as given here. Use a calculator to determine whether the experiments have shown Einstein's formula with an accuracy of 1 part in 10 million. Use the data in figures 1 and 2. Okay. Well, we just need to have to show that this delta M given here is this mass difference is equivalent to this energy here, the energy of the two photons. So we just need to calculate the delta M times c squared. So this is the measured. So this is the 9.096 da 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 da. So this is, yeah, this substitute is and this is given in the mass constant. So it's that 9.906 da 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 times, is the mass constant also given here? What do you call it, atomic mass unit? Yeah, it's given here. Then times c squared. So this we can do by our calculator again. Oh, and we also want to do this in EV. So delta m times c squared is just this whole expression times, well, let's make clear, I mean the whole expression here, just don't want to repeat it, times or divided by then the elementary charge. Okay, and now I can put all this in the calculator. 9.0967794. Then times u here, 1.6605388 equals, now I multiply by the speed of light squared, 2.9979246. And this whole thing I want to square. And then also, since I'm dividing by e, I can enter that. Parenthesis close. And that's completely wrong. What did I do here? Ah, cut back, cut back. Okay, we put it in our calculator. 9.0967794. That's the mass in terms of the mass constant. And I need to multiply by that. 1.6605388. And I need to multiply by the speed of light squared. Just put parentheses in case. 2.9979246 times 10 to the power 8 squared, parenthesis closed. So that's this. And now I'm going to divide by, yeah, this would be the answer in joule. I'm just going to divide by the elementary charge here. So this divided by 1.6021765. And I get, put it in scientific notation, 8.47359582341, 2, 3, 4, 5, 6, 7, 8, 9, 10. I already kept 11 here, times 10 to the power 6 EV. And let's see, 4759, 473598, 1, 2, 3, 4, 5, 6, 7. Well, they ask one part in 10 million. One part in 10 million. So 10 million is 10 to the power 6. It's 10 times 10 to the power 6. So you talk about 7 significant digits. This would be 8.4735912345 6 to 7 digits, right? 7 digits. 6 times 10 to the power 6 EV. In one of the two experiments mentioned, the researcher needed a neutron source to carry out the experiment. Well, in the first experiment, the mass difference was determined by frequency measurement, by ionizing them and accelerating. So this doesn't need any neutron capture. But the second experiment would require actually the capture of the neutrons so that these gamma rays are emitted. So yeah, it should be the second experiment. That's kind of trivial. You need neutrons to get the photons emitted and the energy released. So yeah, that ends the exam then. It's pretty tough, I would say, from the calculation perspective. It's very easy to make mistakes. So this suggests that if you have sufficient time, just to go over the calculations and double check everything.